is probably going to be our final class. Okay. Because next week, Thursday and Friday will be the online presentation for your assignment. So just a quick briefing on the online presentation. Okay. So it's going to be online. There's about, I don't know, there's 15, 16 groups to present. So quite a lot of you to present. Okay. So that's why I needed both sessions lah. Okay. The Thursday, some of you will present on Thursday, some of you will present on Friday, but everyone has to be present. Okay. All group members have to be present. All right. So, but I only need one person from each group to present because we don't have enough time. Okay. We can't keep switching speakers. Yeah, we don't have time to switch around with the speakers. Okay. So everyone has to be present, but only one person from each group will present. Okay. So between the 3 or 5 of you, you choose one person, okay, to present your findings. Now, in the presentation, I don't want to see calculations. Okay. So normally in engineering presentations, you don't present calculations. Okay. Normally when you do presentation, you're actually presenting to client, architects. They don't care about your calculations. They care about your solutions. So you present your solution to me. Okay. So you show me your architectural plan, and then you show me your structural plan. You tell me where your columns are, where your beams are, where your slabs are, what the sizes are, how much reinforcement is in them, and then that's it. Yeah. No calculations, huh? Okay. So each group will have 5 minutes to present. Okay, and then 1 or 2 minutes for question and answers. So all together, and then maybe another minute to switch to the other group. So all together, you have about 8 minutes per group. Okay, 5 minutes to present, 1 to 2 minutes Q&A, and then another minute to switch between groups. All right. Okay, so that's for the presentation. And then the week after, which I believe is your final week, we are going to have a test. Okay, test 3. I just realized we've only had 2 tests, and you guys are supposed to have 3 tests for this course. Okay, so I've arranged for a test in the final week, test 3. Okay, it will be on shear. It will be very, very similar to what I taught you before. All right. Okay, so that's that. So can you see my screen?
Can, Doctor.
Okay, great. Okay, so I'm going to start with the class now. Okay, so fine. So we've done beam design. So for beam, we've done flexure, we've done shear, we've done column design. Okay, so the final thing I want to cover here with you is something related to foundation. Okay, now foundation design, I could have taught you power cap design, but actually power cap design is very, very similar to beam design. Well, in fact, a power cap is a beam. Yeah. So okay, maybe I'll just do a quick explanation here. Right, beam. So when you do a beam design, you design a beam. The beam spans between 2 supports, and then it may carry some sort of load on top. That's a beam. All right. Now, power cap, the way you design power cap is actually very similar to a beam. A power cap is a short beam, basically. Okay. So when you design a power cap, what does a power cap do? Okay. First of all, what does a power cap do? Why do you need a power cap? Do you know what a power cap? Yeah.
Transfer the load from the building to the hard ground.
That is power.
Oh.
Yeah, the power does that. The power cap doesn't do that. Yeah, so it's like this. Okay. Yeah, but good attempt. Thanks for answering. Yeah. Not very accurate, but I'll accept it. All right. So what happens is like this. So in your building, you have your columns, you have your beams, and then you have your columns. Okay, so that's your in a simplistic way, that's your building. Okay, now and then it sits on the ground. Yeah, it sits on the ground. Yeah, so that's the ground. Okay, right. Now, like you say, load from the building has to get transferred into the ground. Yeah. Okay. So the way we transfer the load into the ground is using, we can use spread foundation, spread footing, but normally in Sabah, spread footing doesn't work because the soil in Sabah is very weak. So spread footing doesn't work except for very, very light structures. Yeah. Any substantial structure like a house, you need piled foundation. Okay. So we'll just focus on piled foundation. Okay. So so you have your column. So that's a column. Now to transfer the load from this column into the ground, you need piles. Okay. Now, very often, one pile is not enough. One pile is not enough. Okay. Normally, to support one column, you need 2 or 3 or 4 piles. Okay. So this is your pile that goes down to the rocks, the rock bearing strata. So let's imagine you have 2 piles. Okay. You have 2 piles to transfer the load into the rock or the soil strata, the strong soil strata. Okay. So you see the problem here? You have one column, but you have 2 piles. How are you gonna connect them together? Yeah, because it's only column, there's only one, but piles you have 2 or 3. How are you gonna connect them together? You need something in between. You need something in between to share the load. So that what happens then is the load from the column goes into the pile cap. Half of it goes into the left-hand side pile. Half of it goes into the right-hand side pile. That's what the pile cap does. So this is called the pile cap. Okay? Because the reason why we need a pile cap is because normally we have 2 or 3 or 4 piles. So, and there's only one column. So that's why you need a pile cap to spread the load between the 4 piles. Okay? To spread load to all the piles on the column. Okay? So yeah, that's what a pile cap does, to spread the load to all the piles under the column. Now, so if you look at this, if I draw the structural diagram for this pile cap, it's actually like this, with a pile here and a pile there and a load there. Does that look like a beam? That's actually a beam. Yeah, it's actually a beam. It's a very short beam. Okay, it's essentially a very short beam. You can design it like a very short beam. Okay, so that's why pile cap design, I'm not going to teach you. Okay, if you know how to do beam design, you should know how to do a pile cap design. All right. So today, what I want to teach you is something more interesting. Okay, something more relevant to the problems that we face in Sabah. Okay, which is normally writing is a problem on this tablet. Wait, I have to adjust my angle. Okay, which is retaining wall design. Okay, this one's more interesting, more important, and more relevant. That's why I want to cover it. Okay, retaining wall design. Okay, so as you know, when was it? When was the big rain that we had? Was it November or October, where we had the landslides and everything, all the problems in Sabah? November, October
Early this year, I think March,
Bilang?
February, March, February, March.
Oh, so long ago, Sudaga.
Yeah.
Oh, okay. Wow. Okay, time passes very quickly. All right, yeah. Yeah, we in Sabah we've had heavy rains in the past, okay? And it's caused landslides, things like that, okay? So landslides are basically caused by unprotected slopes. So when you have a slope, like that, okay, what happens is why does landslide occur? Landslide occurs when there is a slip plane that forms in your slope. So let's say that's your slope. Okay, when the weather is dry, landslide doesn't occur. It normally occurs when there's water. Water is the biggest culprit in landslide. When it's dry, the slope is stable. But when it rains, the water permeates into the soil. Now, as you know, in soil, okay, now as you know, in soil is normally in layers. Okay, some layers are permeable, some layers are not so permeable. So what happens then is you have a few different landslides. The one I'm talking here is maybe the translational type. Okay, so what happens here is imagine you have two layers of soil. This one permeable, the one under impermeable. Okay, so I'm pretty sure you've learned this in your geotech. Okay, so what happens then is water enters the permeable part, but it cannot enter the impermeable part. So then it will flow down the face of the impermeable part. So you can imagine when water flows down that face, it creates a slip plane, and eventually that whole chunk will slide. Yeah, this is translational landslide, if not mistaken. Okay, there are other types of landslide. I'm pretty sure you know if you take classes with Dr. Jordan or Dr. Naza. There's another type where it forms a slip plane. It forms like a curved slip plane. Okay, there's this type as well. Okay, very similar mechanism. Okay, so to stabilize slope, normally there are a lot of solutions. You can use geotextile, you can use nails, okay? Or one option, if you have to cut the slope, if the slope has already failed, let's say if the slope has already failed, let's say you end up with a slope like that, okay? Let's say you have a slope like that. Half of it has already failed, so maybe that part has failed. What you have to do to stabilize it then is, one very common way is you build a retaining wall, okay, to stabilize it. Now, it's not just due to landslide. Sometimes if you're constructing a new house, if you're building new development, you may want to cut the slope as well to maximize the land that you can build on. You cannot build on sloping land. If you want to build a house, you have to build it on something flat. So that's why sometimes you have to cut the slope to maximize your flat land to build your house. So then in that case, you need a retaining wall as well. Okay. There are lots of retaining walls, lots of different types. You have shape pile retaining wall, you have concrete retaining wall. But obviously, in this topic, we are talking about reinforced concrete design. So I'm going to cover concrete retaining walls. Okay. So concrete retaining walls normally look like this. Okay. So concrete retaining walls normally look like this. Okay. It has. So yeah. So just some terminology. I just want to share some terminology with you. So concrete retaining wall, normally it's an inverted T like this. Yeah. I call it the inverted T. Yeah, because T is like that. Inverted T is like that lah. Okay. So concrete retaining wall is normally an inverted T. The vertical part is the actual retaining wall. This is the wall, or sometimes we call it the stem. Okay. The bottom, we call it the base. Okay. And then the retaining wall, you can split it in half. The part with the soil, the part where you are retaining the soil, is called the retained side. Yeah. This is where you're retaining the soil. Okay. Now, in terms of the base, you can split it into two terminology as well. Okay. So the base itself, the front of the base, we can call it the toe. The back of the base, you can call it the heel. Okay, so this is some further terminology that normally we use in retaining wall design. Okay. Now, a very important aspect of concrete retaining wall is, so retaining wall, what is it retaining? What type of loading? Yeah. So normally, like when you design a beam, when you design a slab, we always find out what the loading is first, the actions. So in a beam, you have your permanent action, you have your variable action, your dead and live load. Okay, so retaining wall, you also have your actions. What are the actions of the retaining wall? Okay, actions on retaining wall. Okay, so let me just quickly draw the retaining wall again. So this is the retained side. Okay, so what are the actions on the retaining wall? Well, obviously, the very obvious one is you have the soil. Yeah, you have the soil. You have the soil pressing on it. Okay, you have the soil pressing on it. What else? Anyone? So the soil will. So the way the soil exerts pressure on the retaining wall, it exerts pressure in a triangular shape. So it's a triangular UDL that is horizontal, pressing on the wall. So it's trying to overturn the wall like that and also push the wall horizontally. So there are two actions, overturning and sliding. Okay. So soil is one. What other loading do you get? Anyone?
Dead load, the structure itself.
Yeah, you have correct. You may have dead load of the concrete itself. What else? I mean, the actions that can cause the wall to fail. So the soil can cause the soil to fail. What are the loading? Well, you can have your variable action, right? The retained side, the soil. I can have people here. I can drive my car and park here. Correct? Yeah. I can have loading on top of the retained side, right? Yeah. I can have loading that. That loading is called surcharge. Surcharge loading on the retaining wall. Okay. So surcharge loading is normally also a vertical UDL. Okay, but it's a linear, it's not triangular. Okay, so surcharge. What other loading? if it rains. Now, have you done geotech before? Guy? Have you done geotech already?
Yes, yes.
Yeah. What other loadings there? Have you heard of pore water pressure?
Yes.
Yeah. So you can have groundwater in the soil. In the soil, you can have a standing groundwater table. You can have water trapped in the soil. That water can cause pressure on your retaining wall as well. So that water will cause also another horizontal pressure. Okay, on your retaining wall. So we call it pore water pressure, PWP. Okay, so there are three loadings. Pore water pressure, surcharge plus soil. Okay, that's very typical lah. You can have others as well, but this is the most common one. Okay, so actions on retaining wall. The biggest one is obviously the soil pressure. Normally, the second biggest one is pore water pressure. This is due to groundwater table. The third one, sometimes you have, sometimes you don't. Surcharge load on top. Okay. So three loadings, three types of loading. Okay. So we are going to do a quick exercise. Okay. Quick design exercise on how to design retaining wall. So, okay, never mind. I wanted to say something, but I'll tell you later. Okay. Right. So how do you decide what is the have you done this calculation before in GeoTech?
Yes, we did.
You've done before, right?
Yeah.
This soil pressure is actually what's known as in your GeoTech effective. What's the word? Effective stress, I think. Yeah. The formula is the soil density times the height of the soil times what? There's a coefficient. What coefficient? There's a coefficient. Siapa masih ingat? Who can remember? The person who gives me this, tells me what that coefficient is, will get full marks for test 3. Next, in 2 weeks' time. Effective stress. Soil density times height times what? What coefficient is this?
Right moment.
No, before you calculate the moment, there is a coefficient that you have to calculate. What is the name of that coefficient? There's a name for it.
Earth pressure.
Yep. Well, I'm calculating earth pressure. There is a coefficient. What is the name of that coefficient? It's something to do with earth pressure. Okay, never mind. Does it ring a bell now? Ka, Kp?
Yeah.
Ka is on the active side. Kp is on the other side. What is Ka? Active.
Active.
Active what?
Active coefficient.
Yeah, active coefficient. Yeah. So you have your, and the formula for Ka is, if not wrong, I can't remember, 1 minus sine theta over 1 plus sine theta. Is that correct?
Yes.
And then
Yes.
yeah. And then Kp is 1 plus sine theta, 1 minus sine theta. If I'm not mistaken. I don't know. I'm not a geotech engineer. This is what I can remember from long time ago. Yeah.
It's
so
correct.
yeah, it's correct. Okay, thank you. Yeah. So you have the active earth coefficients. That's the one. Active earth coefficients. Yeah. So you have these coefficients. So these coefficients times your height times your soil density gives the effective stress. All right. So normally when you design retaining wall, you need to know the soil properties. The soil properties you need to know is the soil density. So let's tackle an example. Let's tackle an example now. Let's do an example. Let's say let's tackle an example. Let's say I have a retaining wall. Let's say I have a retaining wall, and it's retaining. It's retaining 3 meters. Okay, it's retaining 3 meters. So water table, let's say the water table is somewhere there. Groundwater table. Okay, groundwater table is 2 meters, and then you have another soil on top 3 meters. Yeah, like that. Okay, so the overall retained height is 3. The groundwater table is 1 meter below the ground surface. Okay, so the soil properties, the soil density, let's say 16. The theta, which is the soil angle of friction, let's say 30 degrees. 30 is common. Okay, well, 30 is common for relatively weak soil. Okay, towards the weaker side, Okay, so what else? Yeah, I think that's all we need. Okay, in this case, do we want surcharge? Yeah, let's put surcharge. Let's say there's a surcharge of 5 kilonewton per square meter. So this surcharge is whatever loading you have on top of the retaining wall. Could be cars, could be people walking, yeah, some variable action. Okay. So normally you need to allow for a bit of surcharge. Okay. All right. And then let's imagine, so 3 meters retaining wall, normally 200, let's say 200 thick. Okay, the stem is 200 millimeter thick. Okay, we use concrete grade C30, 35. Okay. All right. So let's design this retaining wall. So the first thing is you have to calculate the earth pressures, which I think you learned during your geotech. So I'm going to go through this very quickly. Okay. So pressures. So there's going to be 3. There's going to be your soil or your earth pressures, and then you have your water, and then you have your surcharge. All right. Now, your soil is 3 meters deep. What would be the soil pressure at the bottom? It will be the density, 16, times the height, which is 3, times the Ka. Ka, how much? Well, if it's 30 degrees, 1 minus sine 30 divided by 1 plus sine 30. How much? 0.33, if not mistaken. Can you calculate for me? 1 minus sine 30 plus, divided by 1 plus sine 30. 0.33?
Yes.
Yeah, 0.33. Thank you. Okay. So your coefficient is 0.33. So 16 times 3 times 0.33. 16 times 3 times 0.33. 15.8. So this will be kPa per meter. Yeah. Yeah. Okay. So this you need to add on to the pore water pressure. Now pore water pressure starts at 1 meter below ground level. So it's smaller. It's a smaller triangle. Okay. And it's only 2 meters high. So water density, we take it as 10 times 2 times, what pore water pressure do you have to multiply by Ka? I can't remember. Do you have to multiply by Ka or not? I think you do, but I forgotten. Anyone, can you help me? Water pressure, do you have to multiply by Ka or not? Earth pressure, yes. Oh, surcharge can multiply as well. Alamak, this this example doesn't have water. But I think you do. I think you do. I think you do. Tell me if I'm wrong, eh? If I'm wrong, tell me. Okay, and then your surcharge is just linear. It doesn't depend on the height. It's just the surcharge was 5 just now, kan? Yeah, 5. Wait. It starts here, goes up to there. So surcharge was 5 times the Ka. So surcharge is 1.65. Okay, so there. Those are your pressures. Those are your pressures. So from the pressures, you have to calculate the resultant force. Yeah, because all of these are kPa. You have to find the force so that you can then calculate, like what Hussam said, the moment. Okay, so pressures. So now we want the force. So I'm going to do the force in red. Okay. Okay. So in red is the resultant force. Now, so let's start with the soil. Now, the soil is a triangular UDL. Triangular UDL, where is the resultant force? 1/3 from the bottom, right? Agree?
Yes, 1/3.
Yeah,
Yes.
1/3. Correct. Thank you. Thank you. 1/3 from the bottom. So 1/3 means 3 divided by 1 to get 1/3, so 1 meter. Okay, that's your resultant. And Fs, I'm going to call it Fs lah, resultant force of soil. So how do you get Fs? It's the area. Fs is the area of that triangle. 15.5 15.4 times the height, 3 meters, divide by 2, because it's triangle, 23.8. Okay, that's the resultant force of the soil. Now, for the water, same, 1/3, but it's only 2 meters. But the water, the triangular stretch block for the water is only 2 meters high. So 1/3 of 2 meters is 0.67 meters. The water, let's say FW, the resultant force is, again, the area of that triangle, 6.6 times 2 divided by 2, 6.6. And finally, for surcharge, now surcharge is UDL, it's not triangular. So it's a rectangular stretch block. So it's going to be in the middle. If it's in the middle, halfway, at mid-height, at mid-height, so it's 3 divided by 2, so 1.5 meters. So, and the resultant force, let's call it Fs, kita ada sudah, Fw pun ada, call it F, ada surcharge C lah. Okay. So FC is 1.65 times the height. Yeah, height 3. You don't divide by 2 because it's rectangular, 4.95. There. Those are your forces, resultant forces. Okay. Now that you have your forces, you can calculate your moments. Okay. So all these forces, they are acting on your retaining wall. Yeah. So let me redraw the retaining wall. So basically what you have is you have a force here at mid height. That is your surcharge punya. So that's your Fs. And then you have your FC, that's FC at mid height. Surcharge. And then you have your Fs. Fs is 1 meter down. And then you have your Fw, your water, which is 0.67. So you have these 3 forces pushing. You have these 3 forces pushing on your retaining wall. And it will cause the retaining wall to do 2 things. It will cause the retaining wall to rotate. It will cause the retaining wall to slide. Okay? It will do both things. All right? So now we have to get the moment. What is that moment? How do you calculate a moment? Well, you have your lever arms already. Okay, now, so to get the moment, we first need we have one height missing, that one. The thickness of that base. So normally the thickness of the base, we follow the stem. If the stem is 200 thick, the base, we make it 200 thick as well. So make it 200 lah. Okay. So now you can basically calculate so now basically you know your moment lever arm. So you take moments about at the bottom of the base, you can calculate your moment. Okay, your rotational moment. So your moment is okay. How do you calculate the moment? I don't want to show you. I want to ask. How do you calculate the moment? Now, think about it. You take a good look at this. What is this actually? How do you design this? Okay. So this is what I was gonna tell you earlier, right before we started. So now is the correct time to ask, I think. If you design this retaining wall, how would you design it? So if you think about it, this retaining wall is actually a what? Now, this retaining wall, can I turn it around? I can turn it around. I can turn it around to make it clearer. Basically, I turn, I just rotate. I rotated the retaining wall. I rotated the retaining wall by 90 degrees. And then you have force here, you have force here, you have force here, right? Yeah. Yeah. What does that look like to you? So basically,
Beam and column.
correct. A beam with column. Your base now becomes a column. Your stem now becomes a it's actually a cantilever beam. Your stem is actually a vertical cantilever beam. Yeah, it's actually a beam cantilevering from a column. So now to calculate the moment, you assume the whole thing's cantilevering lah. Yeah. So to calculate the moment, you treat this as fixed support. You take that as a cantilever, and then you take your load here. Cantilever. Now do you know how to calculate the moment? Yeah, so this is what WSC. Okay, so this is FW FC. This distance is 0.67. This distance is 1. This distance is 1.5. Yeah. Very easy. Wait. Sorry. It's not. I forgot. You have the 0.2 here. To the support is actually 0.2. Another 0.2. So all of them, you have to add 0.2. You have to add 0.2 to go to the end of the support of the beam. Okay? So moment, you treat it as cantilever beam. Moment is FW times 67 plus 0.2, 0.87 plus FS times 1.2 plus FC times 1.7. Okay? FW is what? What's the value of FW just now? FW 6.6. So FS 223.8 times 1.2. Yeah. Plus FC 4.95. There. That's your moment. You treat it as a cantilevering beam. Yep. So 6.6 times 0.87. 6.6 times 0.87, 5.7 plus 23.8 plus 4.95, 8.4. So that's your moment, yeah?
28.7 plus 28.6 plus 8.4.
There, your moment is 42.7. Okay, that's moment. Now, you also have shear. Yeah, because as I told, as you told me, this is actually a cantilevering beam. So FW, FS, and FC is causing shear there at the support. Yeah, causing shear. It's causing shear there because all these forces have to get transferred into the column as shear. So the shear force is FW plus FS plus FC. Which is 6.6 plus 23.8 plus 4.95. Yeah. 6.6 plus 23.8 plus 4.95. 35.35, so 35.4. There. You have a moment, you have a shear force. Do you know how to design the wall of the retaining wall now? You design it as a beam. You just design it as a beam. Yeah, so it's basically a cantilevering beam with that moment and that shear force. So let's do the fracture design, okay? So the in other words, let's deal with the moment first. So we deal with the moment first. Okay? Okay, so beam design. For moment, fracture, what do you start? How do you start? You always start with this formula, K equals to M over B D squared F C K. Yeah. If you look back for the beam design, the flexural design part, flexural calculation part, bending, you always start with this formula first. So moment is 42.7 kilonewton meter. We have to convert to Newton millimeter, so times 10 to the power 6. B, okay, B, okay, BD, okay, this one I need to explain a little bit. What is the B, what is the D, okay? So, a wall. So the retaining wall looks like this. Okay, in cross section looks like this, but in 3D, it's actually a continuous wall. Yeah, your retaining wall is actually a continuous wall. It's actually a continuous wall. All right. So in other words, you design it like a slab. A slab is continuous as well. Okay, so the way you design it is like a slab. You take you design for 1 meter segment. Okay, whatever reinforcement you have, you spread it all over lah. Every meter you have the same reinforcement. Okay, so the B you take 1,000. Yeah, 1 meter. Okay, and then the D. So I told you just now the thickness is 200 of the wall, but that is the H, the thickness of the wall. Okay, you obviously will have reinforcement
So it's going to bend this way. So reinforcement is going to be here. You need to have some reinforcement here. Okay. And you need cover. So let's say we've done the cover calculation 40. So therefore, your D is your thickness, 200 minus the cover, 40. So 160. Okay. So your D is 160. Squared times FCK, 30 just now, given in the question. So that 42.7 divided by 1000 divided by 160 squared divided by 30, concrete grade. So no, only 2. 1, 2. No. 0.06. 1, 2. Yeah, 0.06. Okay, which is less than 0.167. Therefore, no compression reinforcement required. Okay, then you can calculate your Z, which is D times 0.5 plus square root 0.25 minus K divided by 1.134. So D is 160. 0.5 plus. All this formula you should know. I've covered it before. Okay. Minus K is 0.06, 1.134. So all these formula are actually from your beam design, from your flexural design exercise example that I covered at the beginning of the course. Okay, they are the same formula. Okay, bending is bending. Doesn't matter whether it's column, whether it's beam, whether it's a retaining wall. Bending is bending. You use the same formula. You use the same bending formula. Okay, okay. So here. So what is this? Okay, so 0.06 divided by 1.134 minus 0.25 square root plus 0.5, 0.94. 0.944 times the 160. So if I multiply this by 160, it's 151 millimeter. Okay, so my Z is 151 millimeter. So area required is M divided by 0.87 FYK Z. Yeah, yeah, I think so. Yeah, Z. Yeah. Okay, so for the 2.7 times 10 to the power 6. So all these steps, if you don't know what I'm talking about, you go back to the earlier classes. Okay? I've gone through the exact same formula. Okay? Z is 151. So area of reinforcement required. Not much. 650. But this is per meter. Yeah, per meter. So every meter width of wall, you need 650 millimeter square of reinforcement. Okay. So that's the flexural part. Now shear is shear. You've done it before. Okay. So shear, you've done it before. It's the exact same type of calculation for shear. So have a look. Go back and revise your shear because there's going to be a test in 2 weeks' time as well. Okay. So the shear part, you just go back and revise the shear calculation. Okay, it's the same calculation. All right. Okay. Any questions on retaining wall design? Now, obviously, this retaining wall design, I'm teaching you the structural design calculation. This is the structural. In other words, how much reinforcement you need to put in, how thick the wall needs to be. There are two calculations that you need to do for retaining wall design. Two types. I can't spell properly after the New Year. After Christmas and New Year. Ate too much and drink too much. Okay, retaining wall design. There are two types of design that you need to do. The one that I taught you is structural. Structural, the wall itself. The one that you learned in geotech is, well, obviously the geotech. Yeah. You also have to do geotech check. This one I'm not going to teach you. I'm teaching you structural part. Geotech, you have to refer to geotech lah. Okay. What are the but just for your revision, what are the geotechnical checks that you have to do for the retaining wall? What are the geotechnical checks that you have to do for retaining wall? Have you done retaining wall design in geotech?
Yeah.
Yeah. So what are the checks that you have to do? Geotechnical checks.
Sliding
Correct.
and overturning.
Sliding and overturning. Yep. And then there's FOS, right?
Yes.
Yeah. Overturning FOS is normally 1.5, I think.
Yeah.
Sliding FOS normally 2, right?
Uh-huh.
Yeah. Okay. That's one. And there's another check you have to do. The ground bearing pressure, right?
Yes.
Yeah. Make sure the ground, if it's bending, like this. Wait, let me draw my sliding up here so that it doesn't confuse. Yeah, sliding. Okay, sliding. Yeah, so overturning and sliding. But there's also one more check that you have to do. It's because when it overturns, what's going to happen is it's going to put a lot of downward force in the soil at the right hand side. At the right hand side, it's going to put a lot of force into the soil. And then as you go towards the left, that force reduces because it overturns. Yeah, you have to find out where the center of gravity is. Okay, but it's going to look like this. Okay, so you have to check. It's going to cause a bearing pressure on the soil. So that pressure there, whatever the value is, you can calculate. You have to make sure it's less than the soil strength. Okay, you have to make sure it's less than the soil strength. Otherwise, you will get excessive settlement. Okay. In other words, your retaining wall is going to start rotating, moving. Okay, it's going to start failing basically. Okay, so these are the geotechnical checks. What I'm teaching you in this course is the structural check. So, okay, so when you do retaining wall design, you have to do both checks, structural and geotechnical. All right. Okay, so that about covers it. That about covers it for retaining wall design, the structural part. Okay. Any questions?
Is this not in exam, right?
I don't know. uh, you better learn it first. Okay, better learn it. I will let you know about the exam during the revision class. Okay?
Okay, doctor.
Ya, belajar saja. This is very important, especially when you start working. Okay? I will let you know about the exam during the revision class in 2 weeks' time, maybe. Yeah, after the shear, after test three. After test three, I will go through the exam with you. Okay? I'll give you a short revision class on what to expect during the exam. Okay?
Okay.
All right.
Sorry, doctor.
Yep.
I just have a question. For FS, how is the value 23.8?
Oh, FS, huh?
Yeah.
Let me see. But did I calculate it wrongly? I don't know. Are you asking me how I calculated it, or are you saying it's wrong?
Um, I don't want to say it's wrong, but isn't it supposed to be multiplied by 1 meter only?
No. Okay, so FS 23.8, right? You're asking this
Yes.
one, right?
Yeah.
Okay, it's okay. I'll go through with you again. Oh. Okay. Now, so this 1 meter, very good question. Yeah. Yeah. Thanks for asking. So this 1 meter is the height at which the Fs reacts. It's a resultant force. Where the resultant force is. It's a location of the resultant force. It's 1 meter from the bottom. Okay. Now, Fs itself is the resultant force. To get the resultant force, maybe I write it like this. So Fs is the area of the triangle. It's not clear. Fs is the area of this triangle. So you try to calculate the area of a triangle. What do you get? So the area of that triangle is what? Area. So the area of the triangle, now the bottom is 15.84. At the bottom is 15.84. So the area of the triangle is 15.84 times the height, which is 3 meters. And then because it's a triangle, you have to divide by 2. That's how I got it. But first of all, do you agree? The area is 15.84 times 3 divided by 2?
Yes, doctor.
Okay, yeah. Okay, so we try to do that. Yeah. So I got 23.8.
Okay, doctor. Okay,
Yeah.
thank you.
Yeah. So Fs is area of the triangle. Same as the pore water pressure. Fw is the area of that triangle. And then for the surcharge is the area of this rectangle for the surcharge. Is area of this rectangle. Okay. That's all. So yeah, that's how I got it. Okay. But yeah, good thing you asked for clarification. Yeah. Anytime you are not sure about anything, you should ask. Well, I'm still here. Rather better than you go back, you do revision, and you start guessing. Is that right? Is that wrong? Yeah, might as well ask me now. Okay, any more questions? Wow, Everyone else understand ga? No questions ka from anyone else? Zul, you okay?
Okay, Doctor.
Semua faham?
Um,
Oh, okay, okay lah. All right. Okay, so in that case, okay, that's it lah. That's it for retaining wall design. So just to recap, for next week's presentation, we will take turns group by group randomly. Okay, there's not going to be a sequence. I will call each group randomly to present. Some groups will present on Thursday, some groups will present on Friday, but all groups have to attend the presentation, okay, on both days. Okay, so let's say on Thursday I call group 1. Example. No. Let's say on Thursday I call group 5. Okay, so on Thursday presentation I call group 5 to present. All the members have to be there, but you choose one person to present. Okay, all the groups you choose one person to present, to represent you, but everyone has to be there. Even though the group leader is presenting, everyone else has to be there. Okay, I will ask. So the presenting person, before the presenting person presents, I will ask him who is in his group, and I will take attendance for that group to make sure everyone's there. Okay, if someone's missing, then that person will not get any marks for presentation. Wait, presentation heavy, 10% for presentation. So make sure you're there. If I call your name, you're not there, you lose the 10% straight away. Okay? So only one person needs to present, but all the group members have to be there. You have 5 minutes to present, and then you have about 2 minutes for Q&A. I will ask 1 or 2 questions. During Q&A, anyone can answer. Doesn't have to be the presenter lah. Okay? If the presenter cannot answer, someone else in the group can help to answer. Okay? So about 2 minutes for Q&A, and then 1 minute to switch between groups. Okay? To switch to the next group. All right? So that's the format of the online presentation. Okay? And then the test, you'll be on shear design. The strut and tie method, very similar to what I taught you during class. Okay? All right. So that's it. If there are no more questions, I'll end the class here. I will see you for the presentation next week online. Okay? Thursday, we start on Thursday. There's going to be 2 sessions, Thursday and Friday. Okay? I'll see you on Thursday first. All right. Where's my Google Meet?